In this video, we'll put everything together we've seen before in expressing the different gradients in a neural network and obtain one efficient procedure for computing the gradients with respect to our parameter, and that procedure is called backpropagation. So now we've seen in the previous video an expression for getting the gradient with respect to all the parameters in the neural network. That expression dependent on the gradient of the hidden layers, which also dependent on the gradient with respect to the output. And so now we'll see how we can put together all of these different expressions to obtain a procedure that will efficiently compute the parameter gradients. All right, so we've seen in the first video how the gradient of the loss function with respect to the pre-activation at the output layer corresponded to this expression. And then we also saw that the gradient with respect to the activation in the hidden layer corresponded to that expression. And then we saw that the gradient of the loss function with respect to the pre-activation of a hidden layer corresponded to that expression. And finally, we saw that the gradient of the loss function with respect to either the matrix of connections or the biases corresponded to these two expressions here. And now we notice that in each case, except for this one, in the expression on the left, it would often depend on the gradient of other parts of the neural network. So the gradient of the weights and the biases depend on the gradient with respect to the pre-activations. The gradient of the hidden unit activations depended also on the gradient of the pre-activations, while the gradient of the pre-activations actually dependent on the gradient of the activation of a hidden layer. And at the output layer also, we had a formula for getting the gradient of the pre-activations at the output layer. So here, the procedure we see, which is the backpropagation algorithm, the idea is to apply these formulas in order so that on the right side here, we always have pre-computed everything to actually compute that expression. So let's go into the steps of the backpropagation algorithm. So first, we assume that we've already done a forward propagation. That is, we've computed, given the input, the value of all the hidden units, all the hidden layers, and the output layer. So we've computed already f of x, and that's because before we computed each of the activation of each hidden layer h of x. And now what we'll do is that we initialize the pre-activation gradient at the output layer, that's layer L plus 1, and we'll initialize it, or we'll set it to the value of what that gradient is, that is minus the one hot vector for label y minus the output layer. And then we'll iterate from layer L plus 1 to layer 1, and we'll perform these updates, these computations here. So first, we'll actually compute the gradient for the current layer. So I'll call k the current hidden layer at which we are during our iteration here. So we compute the gradients of the hidden layer parameters, the parameters for hidden layer k. Hidden or k, because it can be L plus 1. That could be, these could be the parameters for the output layer as well, depending on the value of k. So we can compute this because we've already pre-computed the pre-activation gradient. So we have the value for this. So now we just take the outer product of that vector with that vector, and that gives us the gradient for the weights. And then the gradient for the biases, as we've seen, is just the gradient with respect to the pre-activations. And then we'll compute or propagate the gradient to the hidden layer below. That is, we'll compute the gradient of the loss with respect to the activation for the layer right below, the layer k minus 1. And we've seen that this just corresponds to taking the pre-activation gradient and multiplying that by the transpose of the connections between the current hidden layer k and the hidden layer below k minus 1. And then we'll compute the gradient, but before the activation, so the pre-activation gradient, which we see here, And we've seen that it corresponds to taking the gradient of the activations and then doing an element-wise multiplication with the activation function derivatives at the value of the pre-activation function. And so once we've reached that part of this iteration in the loop, then we now have the pre-activation gradients for k minus 1. So now we're ready to go from a given value of k to 1 to the value of k that's 1 less. So we, for instance, if we started at k, a value of k which is l plus 1, we'd be ready to go at k equals l, and then k equals l minus 1, and so on until we reach the last hidden layer. So this is the backpropagation algorithm, and we see that it actually does the sort of the opposite of the forward propagation. Instead of going from the input layer to the output layer, it goes from the output layer and then goes through the hidden layer in the reverse order, from the topmost hidden layer to the bottom one. Now here's a visual illustration of the computations we have to do when we do forward and back propagation. And this is also going to give us some hits on how we could implement forward and backward propagation. So we can write forward propagation as an acyclic flow graph where we have boxes. So we see the boxes here with the different variables that we have to compute when computing all the hidden layers and output layer and then the loss function. And so initially, we have to set our input layer to some value x. We also assume that we know what are the current parameters of, so these are the boxes that contain the parameters of the current value for the parameters. And then what we do is that we compute the pre-activation for the first hidden layer. We compute that from the input and the biases and the weights of that hidden layer. Then from the pre-activation, we compute the activation of the hidden layer. And then from that and the parameters for the second hidden layer, we can compute the pre-activation for the second hidden layer. And for a two hidden layer neural network, we could then compute the output. And then from the output, we could compute a loss associated with this output, given that the true label is y. Okay, so that actually gives us a nice way of potentially implementing forward propagation. So each box could be an object and would have a forward propagation or fprop method that would take the parents of the box, so the parents of that object, and compute the value of the box. So for this box here, this would be a box that would compute a linear combination of this, this, and that, so the pre-activation. This box would be a type of object that computes a particular activation function from the pre-activation, and so on. So then performing forward propagation would just be correspond to calling the fprop method for each box, for each object, in the correct order from the parents, which have no children, and then computing it for the other boxes for which we have a value for all of their parents, and proceeding forward until we reach the loss function. And then, if for all of these objects we also had a bprop method, then we could compute backpropagation. In fact, we get sort of for free, we get a procedure for computing all the gradients of all of these boxes with respect to the loss function. And this is called actually automatic differentiation. So what in this setting, what the bprop method would do is that it would compute the gradient of the loss with respect to its children. So so we have a bprop method that would depend on the box's parents. So the fprop depends on its children. It performs a computation with respect to its children, whereas bprop would perform a computation but with respect to the box's parents. And indeed, if we go and look back at the formulas for computing the gradient with respect to the pre-activation or the the activation or the parameters, the formula always depends on the parent of these boxes in this illustration here. So in fact, doing backpropagation would correspond to calling bprop, but in the reverse order of the graph. So in fact, we'd start with this box, and then we'd reverse the arrow, And then at this point, we'd be ready to call Bprop for this box here, which would compute the gradient of the loss with respect to f of x. And then from that, we could reverse this arrow, and now we'd be ready to compute the gradient of the loss. But now with respect to this, using the value and the gradient that have been computed at this box here. And we can continue, so like this we could backpropagate the gradients up to w. So the gradients of w would be computed based on the value and the gradients computed here. Same thing for b. And we could continue like this in the inverse order, the reverse order, to get the gradient with respect to everything. We actually don't need the gradient with respect to x because we're only interested in updating the values of the parameters. So for that reason, we don't actually need to continue in that part of the graph. We don't need to compute the gradient with respect to x because for performing backpropagation and training the neural network, we don't need it. Okay, so this is just a few hints on how we could actually, by using a flow graph decomposition of the forward propagation and using in this flow graph objects that have a forward propagation and a backpropagation method, an fprop and a bprop, we could actually get a fairly flexible implementation of forward propagation and backpropagation. And we actually get, from the forward propagation graph, we essentially get a procedure for backpropagating the gradients almost for free. Now, whenever we implement backpropagation and the computation of really of any gradient, it's always a good idea to verify whether we haven't introduced any bugs in our implementation. And one approach for doing that, which is often used, is to compare with a finite difference approximation of the gradient. So the idea is to notice that by definition, the partial derivative of a function with respect to x is taking this expression here, so f of x plus some epsilon minus f of x minus some epsilon divided by the size of this gap between x plus epsilon and x minus epsilon, so 2 times epsilon, and taking that expression and taking epsilon, pushing it towards 0. And of course, we can't do that on the machine, but what we could do is to actually take epsilon and fix it to a very, very small value to sort of get an approximation of the real thing, which would be to push epsilon towards 0. So in our case, what we could do is, in this formula here, f of x would be our loss. X would be one of our parameters, so maybe it could be wij for some hidden layer k. And so computing f of x plus epsilon would correspond to computing the loss, where we've taken the current value of our parameter, but we've added some epsilon value, some very small value like say 10 to the minus 6. And f of x minus epsilon would correspond to, again, computing the loss, but where we would have subtracted epsilon from the current value of our parameter. And so by doing this, we could compute that expression, and that would give us an approximation of what the partial derivative of the loss with respect to our parameter would be. And then so we could compare that value of the estimate of the partial derivative for our parameter with the actual value that backpropagation has computed. And so this means that if we want to test the implementation or the computation of the partial derivative with respect to every parameter, so all connections between all hidden layers and also all biases Bik, it means that we would need to do a forward propagation with plus epsilon and minus epsilon for each parameter. So when we do this computation, this finite difference approximation, for debugging, we actually do it on a very small neural network with very few parameters, few connections, and few biases. And so once we get all the partial derivatives approximated with this finite difference, then we can compare it with the computed gradient, the computed partial derivatives with respect to all parameters. We could look at the absolute difference between the average absolute difference. We could look at the angle between the approximated gradients and the actual gradient we computed with finite difference. And if this difference is very, very small, then we can be fairly sure that our implementation of backpropagation is correct. So that's a very good trick to know about if we want to debug an implementation of backpropagation.